Today we're going to be looking at some of the basics of infrared or IR spectroscopy. First we'll just go through some of the general theory of how IR spectroscopy works. Then we'll look at a basic overview of the IR spectrometer, which is where you're going to record the IR spectrum. From there we'll look at the various signal intensities and why some signals are more intense than others. Next, we'll sort of get into the heart of IR spectroscopy, looking at where the various signals occur in the IR spectrum and what those signals correspond to as far as functional groups and things like that within the molecule. And then we'll just do some examples of how to analyze some simple IR spectra. Okay, the first thing we're going to look at is just some of the general theory behind IR spectroscopy. And here we have a sample spectrum. This is an IR spectrum of ethanol. And you can see along the spectrum we have all of these different peaks going across it. So we want to find out what about this molecule causes these peaks to show up at different regions of the spectrum. So the first thing we want to think about is really the nature of the covalent bonds and the fact that a covalent bond is not static. So if we just do a simple example, we'll use HCl, where the hydrogen and chlorine are bonded by a covalent bond. And we can use the analogy that this bond is kind of like a spring. So the hydrogen atom is connected to the chlorine atom by the spring. And now the spring, we can stretch the spring by adding energy. And for IR spectroscopy, the energy is light. So when energy is put into this, the spring will be stretched. So what's happened here is energy was absorbed. Now, that absorption of energy is what causes a signal to show up on an IR spectrum. So a couple things to consider. First, nearly all compounds that have covalent bonds are going to absorb energy at certain frequencies of the electromagnetic spectrum. And they're going to absorb frequencies in the infrared region. And this IR absorption is quantized. So that means only select energies are absorbed by a particular molecule. And since different molecules are going to absorb different sets of energies, different molecules then have different IR spectra. So if we compare ethanol and diethyl ether, okay, both compounds have covalent bonds, they have carbon, oxygen, and hydrogen, but you can see they have very different IR spectra. And the reason is because the different nature of these molecules, they have different bonds, they absorb light at different energies to give very different IR spectra. Now we can relate energy using this equation E equals h nu, which equals hc over lambda. And of course, E is energy, nu is the frequency, and lambda is the wavelength. And if we sort of compare this to an IR spectrum, down here at the left end, is high energy, and by this equation we can say as energy increases, the wavelength decreases. And then of course on the right end of the spectrum, there's a low energy but a high wavelength. Now when a molecule absorbs IR energy, it's causing an excitation in their vibrational motions. And on the spectrum, we can see that the units are actually reported in wave numbers, which is inverse centimeters. And we have an equation for this. So the wave number is just 1 divided by the wavelength. So a higher wave number corresponds to a lower wavelength. So here where we have high energy, we also have a high wave number. So at the left we have 4,000 wave numbers. Down at the right we're clear down to 400 wave numbers. And again, the units of wave numbers is inverse centimeters. Now a molecule has different normal modes of vibration, and these include stretching and bending. So here we can just see for sort of a CH2 moiety in a molecule, there's actually 6 different modes of vibration. The CH2 can stretch, so we can have a symmetric stretch or an asymmetric stretch, but also the CH2 can bend. So this bond angle can sort of decrease and increase in a bending, and you can have both symmetric and asymmetric bending. And we're going to look at sort of an animation of some of these in just a minute with water. But each of these different stretching or bending vibrations, they occur at a very discrete energy level. And when the frequency of the IR light that's coming through that molecule matches the frequency of one of these stretching or bending modes, IR light gets absorbed, and that's going to produce a signal on the spectrum. So just this CH2 in the molecule should actually have 6 different signals in an IR spectrum. For example, here we're going to take a look at a water molecule, and below it is just a sample IR spectrum of water. And water has these different places where it absorbs IR energy to give these different vibrational modes. So the first one here we'll look at 3727, we can see we have this stretch between the oxygen and hydrogen, and this in fact is an asymmetric OH stretch. Then if we move on to 3607, it's another type of OH stretch, but this is a symmetric OH stretch. So another place where this molecule absorbs IR energy. And then finally down here at 1640, we have a bending. So HOH bending, and this is an in-plane bend. One last thing I want to take a look at is just the y-axis. So we've looked at the x-axis to see what the wave number actually means, but what does this %t on the y-axis mean? Well, %t is just % transmittance. Okay, and what that means is that's how much light is actually transmitted through the molecule. So we see this large signal here that only has about 10% T. That means only about 10% of the light got transmitted, but 90% got absorbed. So that's why this corresponds to a particular vibrational mode, because this is where energy was absorbed, resulting in very little energy transmitting through. The next thing we're going to do is just take a very basic look at the overview of the IR spectrometer and how it works. So modern IR spectrometers are generally Fourier transform infrared spectrometers, or FTIR is how they're commonly abbreviated. And we sort of have a diagram here of how this instrument works. But here's our sample, and down below the sample is a detector. And there's also a light source that's going to get passed through that sample. And what happens here is this light source actually first goes through a beam splitter, and the light beam is split and goes to a stationary mirror as well as a moving mirror. And that split light beam, after it bounces off the mirror, it comes back and these two beams recombine and go down into the sample, or go through the sample. Now this moving mirror is continuously moving, and of course the stationary mirror stays, and this beam that passes through is always the same. Now the light source that's actually being transmitted contains the whole sum of wavelengths. Okay, so we have all of those wavelengths, and what happens is when the light from the stationary mirror and the moving mirror recombine, depending on the position at that time of the moving mirror, that light can combine constructively or destructively. Okay, and this combination actually gives a wave pattern that passes through the sample, and that wave pattern is known as an interferogram. And every wavelength on the spectrum has a different interferogram. If the IR radiation at a certain wavelength gets absorbed when it passes through a sample, then the intensity of the interferogram for that particular wavelength is going to decrease, which then changes the interferogram that exits the sample, and then that's detected by the detector. Now the computer gets that interferogram, and what happens is it's able to decode it to actually produce sort of a traditional IR spectrum. And that decoding actually makes use of the Fourier transform technique. Now, the instrument that we have in our lab is actually sort of a more advanced form of the FTIR, because it has an ATR accessory, or an attenuated total reflectance accessory. What that means is sample preparation is very, very simple. On this plate here, there's a small crystal, generally a diamond, and all you have to do is either place a drop of your liquid or oil sample on that diamond, or if it's a solid, you can put the solid on that diamond and then put this arm over to actually compress the solid down onto it. Now what this attenuated total reflectance does is it's designed in such a way that when light hits this crystal, at least one surface of this crystal allows that light to be reflected back into the instrument, which makes it very, very simple. And then all you have to do is just clean off the crystal with a little bit of solvent, and you're ready for a new sample. The next thing we're going to take a look at is the signal intensity in an IR spectrum. In other words, If a molecule does absorb a certain energy of light and a signal is produced on an IR spectrum, how intense is that signal going to be? Or how much energy does it absorb? So one of the main things we need to consider has to do with the polarity or the dipole moment of a bond. So for a bond to absorb IR radiation, there must be a change in the dipole moment during that vibration. So if a bond is nonpolar because of symmetry, IR light isn't going to be absorbed, and that vibration is said to be IR inactive. So let's compare a couple of alkynes. And specifically, we're looking at the carbon-carbon triple bond stretch. In this first one, we have a terminal alkyne. There's really no symmetry here. We have a good carbon-carbon dipole. So this is going to absorb IR light, and that is going to be IR active and give us a nice signal on the spectrum. However, if we move to this symmetric alkyne, we have a plane of symmetry that runs through the carbon-carbon triple bond. This molecule doesn't have a dipole there, so it's not going to absorb IR light, and this carbon-carbon triple bond is said to be IR inactive. Another thing we can consider is the fact that a larger dipole is going to mean a more polar bond. That also is going to mean a stronger absorption. So here we're going to compare a carbon-oxygen double bond to a carbon-carbon double bond. In the carbon-oxygen double bond, we have a pretty strong dipole going from the carbon to the oxygen. This absorbs IR light extremely well, and it gives us a very intense absorption. However, if we have a carbon-carbon double bond, at least one that's not symmetric, so these could be whatever, R groups coming off the carbon or hydrogens coming off the carbon. Even in an asymmetric system, we still have a carbon double bonded to a carbon. There's not going to be a very large dipole here. That means this IR absorption is going to be much smaller and much less intense. So if we want to compare XH bonds, whether it be oxygen, nitrogen, or carbon-hydrogen bonds, if we have a more polar bond, so OH is more polar than NH, which is more polar than CH, well, this stretch corresponding to the OH is going to be more intense than the NH. And then the stretch corresponding to the carbon-hydrogen bond is going to be the least intense because it's the least polar. Now let's just compare a couple of heptene isomers. And what we'll eventually learn is that the carbon-carbon double bond stretch generally appears around 1650 on the IR spectrum. So that's right around in this region. Now 1-heptene, there's not a lot of symmetry here. We have two hydrogens, it's a terminal alkene, and we actually end up with a pretty strong absorption in the 1650 region. However, when we go to 3-heptene, we still have a carbon-carbon double bond, but this molecule is much more symmetric. And although there's still a little bit in that region, a stretch corresponding to that carbon-carbon double bond is almost non-existent. So that's something you really have to watch out for. Just because you don't see a certain stretch doesn't mean this functional group's absent. That just means it's very symmetrical. This next section really gets us into the heart of IR spectroscopy, and we're going to be looking at different spectra and comparing them with molecules, and we're going to see what these peaks mean and how they can help us determine things about molecular structure. So an IR spectrum can be divided really into two regions, and sort of the region that separates the two is right around 1400 wave numbers. To the left of 1400 wave numbers, so greater than 1400 wave numbers, that is our functional group region. And that's the region we're going to spend the most time looking at. To the right, which is less than 1400 wave numbers, that's called the fingerprint region. We'll be able to get a little bit of information out of this region, but often it's sort of polluted with a bunch of bending frequencies and things like that. So it's often hard to pull specific details out of the fingerprint region, so we'll mostly focus on the functional group region. Now, sort of further breaking down the regions of an IR spectrum, there's 5 basic regions we can look at here. And this first section, here at about 2,500 to 4,000 wave numbers, is the ZH single bond stretches. So that is something bonded to a hydrogen. So some of the common things that we'll see in this region, we have the OH stretch, so alcohols we'll see here. NH stretches, and carbon-hydrogen stretches. So all of these bond stretches are going to show up in this region, and that's going to be very diagnostic for us. In the region of 2,000 to 2,500, that's going to be our triple bond stretches. So alkyne and nitriles are the main ones that we're going to look at. 1,500 to 2,000 is going to be the double bond stretches. So we'll look at carbon-carbon double bonds in this region, as well as carbon-oxygen double bonds, or the carbonyl functional group. We'll see those stretches in this region. Then from 10,000 to 1,500, that's where we're going to see single bond stretches. So that'll be things, carbon-oxygen stretches is one example. And then sort of less than that, again, is that those bending vibrations, which we're not going to really focus on. In a lot of cases, you're just going to be able to sort of use a chart to see where certain stretches for particular functional groups are at. But it's really nice to know what factors influence where the peaks show up on an infrared spectrum. And there's 2 main factors that affect the peak location. The first is the mass of the atoms. So what we're going to see here is that the stretching frequency of a bond to a lighter atom will be greater than the same bond connected to a heavier atom. So here we can compare HCl and HBr. Well, in both cases, hydrogen is the same, but chlorine is lighter, and bromine is heavier. So because chlorine is a lighter atom, it's going to have a greater stretching frequency. So the HCl, that stretch, is going to be at a higher wave number. HBr is going to be at a lower wave number. Now the way I like to think about this, which just sort of kind of helps maybe more as a mnemonic than anything else, but if we compare HCl and HBr, again thinking of this bond as a spring, chlorine is a lighter atom, so if this bond is a spring, the weight of the chlorine is only going to stretch this spring so much. But now if we compare that to the bromine is heavier, so it's going to stretch that spring a little bit further. So now to get sort of a complete stretching of the spring, the HCl bond, this spring, because chlorine was lighter, is sort of a tighter spring, so it's going to require more energy to fully stretch that out. And then you can think of the HBr, with bromine being a little bit heavier, it's not going to require as much energy to fully stretch that spring. So that's one way to sort of think about the mass of the atoms. So since it requires more energy to stretch out the HCl spring, more energy, and again, higher energy also means higher wave number. Then we can also relate the location of the peaks to bond strength. So a stronger bond is going to have a higher stretching frequency than a weaker bond. So if we just look at carbon-carbon bonds, we know that a carbon-carbon triple bond is the strongest. Carbon-carbon single bond is the weakest. So the stronger carbon-carbon triple bond is going to have a higher wave number. And another way we can think about this in terms of springs, think of a triple bond, a stronger bond, you can think of that as being a stronger spring, which requires more energy to stretch. If it requires more energy to stretch it out, then that means it's going to have a higher wave number, because higher energy equates to higher wave numbers. So you can make these analogies for various systems to figure out where things are going to stretch. So now we're just going to go through some of the different functional groups that you'll find in molecules and where you can see these in an IR spectrum. And we're going to start with the most diagnostic one of all, which is the hydroxy group, or an OH. Hydroxy groups are generally very broad, very intense, and usually around 3,300 wave numbers. So they can be anywhere from usually 3,200 to 3,600. Now these are just sort of free OH groups. This doesn't include the carboxylic acid. The carboxylic acid, as we'll see later on, is different. That OH group is going to be closer to 3,000. So this is just OH groups that aren't carboxylic acids. So here's the spectrum of 2-butyne 1-ol. We have this hydroxy group, and this broad stretch, it's around 3,350. That corresponds to the OH, and that's because this OH bond is stretching. It absorbs that energy, giving us this peak on the spectrum. Now we can go through and identify the alkyne and some other things in the spectrum, but we'll get to that later. We're just going to look at specific functional groups right now, one at a time. Okay, so now we're at the carboxylic acid. So again, it's an OH, but it's a different functional group. It's part of a carboxylic acid. And what we're going to see about a carboxylic acid OH stretch is that it's not at as high a wave number as an alcohol. Carboxylic acids are generally centered around 3,000 wave numbers, and in most cases they're even more broad than an OH. You'll also see, in addition to sort of our carboxylic acid stretch, we have some other stuff in here. And these peaks actually correspond to other bond stretches in the molecule. So these are actually carbon-hydrogen bonds that we'll see later. But they're just overlapping, so that's why they look like they're sort of part of the same peak. Okay, the next thing we're going to look at, sort of in that ZH region, is NH and NH2 stretches. So NHs and NH2s, again, they show up in this same region, but they're generally less broad and less intense than the OH stretch, and they appear between 3,300 and 3,500 wave numbers. So just based on the wave number, they're difficult to figure out between an NH and an OH, but sort of by looking at the shape of the peaks, usually it's pretty easy to tell. So here we have an NH2, part of isopropylamine. And you can see that they're in the same region as the OH, but they're much less intense and they're sharper peaks. So you'll generally see that with amines. Now, interestingly, if you have a primary amine, so that means the nitrogen has two hydrogens, you're going to see two peaks in that region. So there's two different stretching bands. Next, if we move from an amine that contains two hydrogens to an amine that contains one hydrogen, such as diethylamine, now we just have one hydrogen. Now we're only going to see one peak in that region. So here's this NH stretch. So again, we're not going to confuse that with an OH because it's just really too narrow for an OH. So this is really telltale of just an NH stretch, so a secondary amine. And again, it's sort of in that 33 to 3500 wave number region. Sticking with the 2500 to 4000 region, we're next going to take a look at the CH stretch. And almost every organic molecule that you look at is going to have carbon-hydrogen bonds, so this is a stretch you should expect to see very, very frequently. All of your CH stretches are going to occur between 2700 and 3300 wave numbers, and we're going to see that they're pretty intense and quite narrow in most cases. First, we're going to look at sp3 hybridized carbon-hydrogen bonds. These appear just below 3000. So 3000 is important here because that's going to be sort of our cutoff for sp3 hybridized carbons and sp2 hybridized carbon hydrogens. So in this case, we're looking at hexane. All of the carbons are sp3 hybridized, and all of these carbons have hydrogens attached. Methyl, of course, has 3 hydrogens, and then these CH2 groups have 2 hydrogens. Well, these sp3 hybridized carbons, they are going to show up just below 3000 wave numbers, and that's what we have right here. You can see that these stretches are intense, but they're also quite narrow, and because there's so many CHs, there's quite a few peaks in this region. Now, if we move from sp3 to sp2 hybridized carbon-hydrogen bonds, carbon sp2 hydrogen bonds appear just above 3000 wave numbers. So that's going to be these hydrogens that are attached to the alkene. That's what we see right here above 3000 wave numbers circled in blue. Now, of course, 2-hexene also has a lot of sp3 hybridized carbons that contain hydrogen, and we can still see those stretches just below 3000. So these sharp, distinct peaks just above 3000 are very diagnostic for alkene hydrogens. Now we're going to move into the double bond region. And the first thing we're going to take a look at is the carbonyl group, C double bond O. The carbonyl stretch is very, very strong. It's very easy to spot, and you'll see it between 1650 and 1850 wave numbers, depending on the nature of the carbonyl. Is it a ketone, an aldehyde, ester, amide? So here's just sort of a table that lists some of these, and you can see, as far as our wave numbers go, that the amide is generally at the lowest stretching frequency. Slightly higher than that is the ketone, then the aldehyde, then the ester, and then at the highest stretching frequency is the carbonyl of the acid halides. First, we're going to look at just cyclohexanone, and we're concerned with the stretch that corresponds to this carbonyl. And here it is right around 1700 wave numbers, specifically at 1710 wave numbers. And you can see it's very strong and very intense, and that's diagnostic for a carbonyl group. Now, one effect that you're going to see is that if the carbonyl is in conjugation with a double or triple bond, the stretching frequency of that carbonyl is going to be lowered by 20 to 40 wave numbers. So here we have a carbonyl that's in conjugation with this pi bond. And of course you can think about the resonance structure for this. Although it's a minor contributor, in the other resonance structure we have a single bond. That single bond character is what causes the stretching frequency to be lowered by 20 to 40 wave numbers. So in cyclohexanone we saw a stretching frequency of 1710. Well, now when this is in conjugation, it's been lowered to 1690, so lowered by 20 wave numbers. And that's a result of this conjugation. That's a result of the single bond character in the carbon-oxygen bond. Now let's take a look at the aldehyde. Again, the aldehyde carbonyls, they're usually a little bit higher stretching frequency than just a ketone, but they're so close it's often hard to discern them. You're going to see the aldehyde stretch, again, right around 1720 wave numbers. Here is benzaldehyde. Now in this case, this could be a little bit confusing because the aldehyde is in conjugation, so that causes the stretching frequency of the aldehyde to be lowered to right around 1700 wave numbers. So that could be an aldehyde in conjugation, or you might be tempted to think that it's just a ketone. But there's a clue you can look for with aldehydes. It's very, very diagnostic. And with aldehydes, you're going to see the aldehyde CH showing two bands that appear 2720 and 2820 wave numbers, which is very diagnostic. Here's the one at 2720, here's one at 2820. They're of medium intensity, they're usually pretty narrow, and they're very diagnostic for the aldehyde CH stretch. Now we're going to move into the triple bond region. We're going to look in that region is where you're going to have carbon-carbon triple bonds and carbon-nitrogen triple bonds. They're very hard to distinguish between, but they generally show up between 2100 and 2260 wave numbers. So here we're going to look at 2-butyne 1-ol. We've already talked about the alcohol OH stretch, which you can see here. But now we're specifically concerned with this carbon-carbon triple bond stretch. The carbon-carbon triple bond stretch isn't all that intense, but it's fairly distinct, and you can see it right around 2100 wave numbers, which is circled here in red. This corresponds to that alkyne C triple bond C stretch. Now, if we move from an internal alkyne to a terminal alkyne, it's going to be much easier to distinguish. First, we have our carbon-carbon triple bond stretch right around 2100. That's this peak right here. But now, because we have a terminal alkyne, we have the carbon-hydrogen stretch. And that's a very diagnostic peak right around 3300 wave numbers. And that's what we see right here. It's much more narrow than an alcohol, so you don't have to worry about getting it confused with the OH. So if you see an alkyne carbon-carbon triple bond stretch as well as an alkyne CH stretch, you could pretty much say that you have a terminal alkyne in your molecule. Now if we look at the carbon-carbon double bonds, they're going to show up in the similar region to carbon-oxygen double bonds, but the main difference is they're not nearly as intense as those carbonyl stretches that we saw earlier. In general, your carbon-carbon double bond stretches occur between 1620 and 1680 wave numbers. And here we're going to look at the stretch for 2-hexene. This stretch corresponds to the carbon double bond carbon. And you can see it right here. So it's right there around 1650. And it's not very intense. So that's how we can say it's definitely not a carbon-oxygen double bond. But because it's in that double bond region, it's probably a carbon-carbon double bond. Additionally, to confirm this, there's a couple other things we can look for. We can look for, in many cases, the carbon sp2 hydrogen bonds, which will show up just above 3000 wave numbers, and that's what this peak here corresponds to. That corresponds to the sp2 hybridized carbon hydrogen stretches. So that helps us to confirm that we have an alkene in our molecule. We can also identify aromatic carbon-carbon double bonds pretty easily in IR spectrum. The aromatic carbon-carbon double bonds are somewhat special, so they show up generally at 3 different regions, although you may not always see all 3 signals. But if you have an aromatic ring, these carbon-carbon double bonds will generally show up one right around 1600 wave numbers. Then you'll have one right at about 1500 wave numbers. And then you can have one just less than 1500 wave numbers. Now sometimes this last one, right below 1500 wave numbers, is hard to see. So you should look for 2 to 3 peaks indicating an aromatic ring. Now we're going to look at a very common single bond stretch that's really easy to identify, and that's a carbon-oxygen single bond. And it's also important to note whether it's an sp3 hybridized carbon-oxygen bond or an sp2 hybridized carbon-oxygen bond, because their stretches occur at different frequencies. So here's just a few examples. Here we have an alcohol. Of course we would be able to see the OH stretch, but there's also a stretch corresponding to this sp3 hybridized carbon-oxygen bond. And that we're going to see somewhere between 10 and 1100 wave numbers. So in this case, this alcohol stretch for the carbon-oxygen bond is at 1050 wave numbers. An ether, once again, we have sp3 hybridized carbons bonded to oxygens. So again, those are going to show up right around 1050 wave numbers. But now if we move to an sp2 hybridized carbon, such as that in carboxylic acids and esters, we've already talked about the carbonyl, but now we're concerned with the carbon-oxygen single bond stretch. Once again, we can think about resonance. So by resonance, this single bond actually has some double bond character that you can see over here. That double bond character results in an increase in the stretching frequency. So if the carbon is sp2 hybridized, the carbon-oxygen single bond stretch is going to be between 12 and 1300 wave numbers. So in this case, 1250 wave numbers for the carboxylic acid, and then the sp2 carbon-oxygen single bond stretch in an ester that's going to occur at about 1250 wave numbers. Now with esters, we also have this sp3 carbon-oxygen bond right here, and that is going to show up as would be expected at 1050 wave numbers. Let's look at an actual example here. Here we have 2-butanol. Our carbon is sp3 hybridized. So if we consider this carbon-oxygen single bond stretch here, we would expect to see that between 10 and 1100 wave numbers. Well, here we see this signal right around 1000 wave numbers. That corresponds to this carbon-oxygen single bond stretch, and that is very diagnostic. Now if we move to an ester, we have our sp2 carbon-oxygen stretch. So that's a result of the bond between this carbon and oxygen, and that's very distinct right around 1250. But we also have the sp3 hybridized carbon, and that carbon and an oxygen will also have a stretch, but that is right around 1050. So very diagnostic for esters. And just to look at something we already talked about, of course an ester has this carbonyl. Here's our carbonyl stretch. One last thing that we're going to look at is the carbon-hydrogen bending vibrations. All of the other frequencies that we've looked at so far have been stretches, but there's actually a couple carbon-hydrogen bending vibrations that are pretty diagnostic and helpful in IR spectroscopy. In general, they're less pronounced than stretching, and because they're found in or around the fingerprint region, they can be hard to identify, but there's a couple that we can pick out here. And for this example, we'll look at 2-hexene. And there's two different bending vibrations that are pretty easy to pick out. The first is just the carbon-hydrogen bending. All of these carbons have hydrogens, so if we just look at maybe this CH2 group here, this can bend back and forth, changing its bond angle slightly, giving us a bending vibration. And for a CH2 or CH group, the bending is going to occur just above 1400 wave numbers. So if there's 1400, this bending you'll see just above 1400. The other type of bending that you can frequently see is when you have a methyl group. Here we have two methyl groups in this molecule, and we can see methyl bending, and those occur just below 1400 wave numbers. So that's what we see right here is the methyl bend. And those can be pretty helpful in determining some of the structural features of your molecule. In this final section, we're just going to go through some examples and pull a lot of information out of different structures so we can see how you might match a structure to a spectrum, and some examples where IR could be pretty useful in distinguishing different compounds. One of the things that students often mistake is thinking that they should be able to deduce a complete structure from an IR spectrum. And for most students that is just pretty much impossible to do. Really, you just want to get a lot of information about the functional groups out of it, just so that you can have some clues as to what the structure is. So let's look at some examples, and we'll go through and figure out some distinguishing features. So the first one that we're going to look at is just this alkene compound. First, we're going to look up here in the 3000 region, and we have a signal just above 3000 wave numbers. Remember, that is CSP2 hydrogen stretches. So that's going to correspond to these CHs on the alkene. But then just below 3000, this is the CSP3 hydrogen stretches. So that's all of these CSP3 carbons with hydrogens on them. So that's where their stretches are showing up. Next, as we move down the spectrum, we have a pretty distinct signal right around 1650 wave numbers. And that is the carbon-carbon double bond stretch. So that's what corresponds to this carbon-carbon double bond. A couple other small things that we can pull out of this have to do with some of the bending motions. Here's 1400 wave numbers, and just above 1400 we have a pretty distinct signal, and that is likely all of these CH2 bending frequencies. And then just below 1400 wave numbers, this is from the methyl groups bending. So we have two methyl groups. So all of these things we can sort of put together and come up with some of the features of this molecule. Next, we can look at this alcohol that has both an alcohol functional group and an alkyne in it. And we can pull some things out of this spectrum. First, the most distinguishing thing in the spectrum is the OH stretch. And that is sort of this broad peak here. That's the OH stretch, right around 3400. Now, because we have a terminal alkyne, we should also see this alkyne carbon-hydrogen stretch here at about 3300. Now, it's sort of buried within this alcohol, but we can see this extra sharp peak coming out of the alcohol peak, and that is that alkyne CH. Now, right below 3000, we have a couple of signals. And remember, just below 3000 is a CSP3 carbon-hydrogen stretches. So that likely corresponds to these CH stretches there. Another distinguishing signal is this peak right at about 2100 wave numbers. And that distinguishes this carbon-carbon triple bond stretch. One last signal to point out here that is really well defined is the signal at 1050. And that corresponds to the carbon-oxygen stretch. So that is an sp3 carbon oxygen single bond stretch. So these are some of the features we can pull out of this molecule and identify within the spectrum. Next we have this amide, and the first thing we see is some sharp peaks right here between 31 and 3400 wave numbers. Now these peaks correspond to the NH2. Remember, if we have two hydrogens on nitrogen, we should see two peaks. And that's what we see right here. We see one that looks to be at about 3150, and one that looks to be at about 3350. Now these are at a slightly lower stretching frequency than what you would see with amines, and that's to be expected with amides. So amide nitrogens, those NH stretches, are at a lower stretching frequency than amines. So that's just something to look out for. Now we should also expect to see sp2 carbon-hydrogen stretches. Remember, those show up just above 3,000, and they're actually pretty hard to see in this spectrum because they're sort of buried under the N8 stretches, but we can see possibly a couple of those peeking through in this spectrum. Another thing that we can identify, which is very diagnostic, is the C double bond O carbonyl stretch of the amide. And that is right here at about 1680 wave numbers. Because it's in conjugation, it's slightly lower than you might expect, but in general, amides are the low end anyways. Another thing that we can point out in the spectrum is the carbon-carbon double bond stretch right around 1600 wave numbers. And that is lower than expected. Again, because of conjugation, this double bond has some single bond character, lowering its stretching frequency. Next, we're going to look at the IR of ethyl benzyl ketone. And there's a number of things we can pull out of this spectrum. First, we'll kind of do our basic cutoff here at 3000 wave numbers. To the left of 3000 wave numbers, these signals are our carbon sp2 hydrogen bonds. And although they're part of a benzene ring, they're still responsible for those stretches. To the right of 3000 wave numbers, this stuff over here, that is the carbon sp3 hydrogen bonds, and of course we have a number of those. The next thing we can look at is this signal right around 1710 wave numbers, and that is our carbonyl stretch, our C double bond O. Because we have this benzene ring, we should have some very specific stretches in this spectrum that represent that. The first is this stretch right around 1600. Then we have one right at 1500 and one just less than 1500 wave numbers. These three signals are representative of an aromatic ring. One other thing we can pull out of here pretty easily is this signal just less than 1400, and that is representative of a methyl group. And that's this methyl group right here. So these are a few of the things that we can pull out of this spectrum. One of the things that IR is often used for is to determine between some similar isomers. Because all of these compounds have the same molecular formula, C4H8O2, but they have different functional groups, so we can use IR to distinguish them. So just a few things before we look at spectra that we should be able to say here. So all have a carbonyl. So in all the spectra, we're going to see a carbonyl stretch, and that's going to be somewhere between 17 and 1750 wave numbers. The next thing we can say is this ester here, we're not going to see an OH stretch. But in both of these two compounds, we're going to see an OH. But the first one is just a regular primary alcohol, and we would expect to see that around 32 to 3600. However, the carboxylic acid OH, we would expect to see that around 3,000 wave numbers. Additionally, with this compound, we should see a CsP3 oxygen stretch. With the carboxylic acid, we won't see any CsP3 carbon-oxygen stretch, but we'll see a CsP2 carbon-oxygen stretch, and then in the ester, we'll see both. So we should be able to differentiate the spectra between these three. In this first one, the first thing you should see, well, there's no OH stretch. So most likely this is going to correspond to the ethyl acetate. Because this compound you wouldn't have an OH stretch. But what we do see, we see the carbonyl, we see some CsP3H stretches. We also see right here at about 1250 the carbon sp2 oxygen stretch, and right here at 1050 the carbon sp3 oxygen stretch. This one corresponds to this bond, and this one corresponds to that bond. The next one we have here, right here around 3400 wave numbers, is our OH. Right here just less than 3000 CsP3H stretches, which we have in this molecule. Right here just above 1700, that's our carbonyl. And then here at about 1050, that is our carbon sp3 oxygen stretch. So those are the main things you can pull out of this one. Our third spectrum must be the carboxylic acid, which we can see here. Now we still have this broad OH stretch, but now it's moved down to about 3000 wave numbers. So we can kind of see it here. And that is diagnostic of a carboxylic acid OH. We also have the carbonyl, which is just above 1700. And then kind of buried in here with the OH stretch here below 3000, again our CsP3 hydrogens. And then you can see here just above 1200, that is our CsP2 oxygen stretch. And that corresponds to our carboxylic acid.